Today we'll start with the sixth lecture of rotational motion. So in this lecture, we'll learn a lot about rolling motion. Okay, what is rolling motion and how do we use that kind of rolling motion in problems. Okay, so the topic or the main crux of our lecture today is nothing but rolling motion. Rolling motion. Okay, we'll understand in a while rolling motion is nothing but a combination of rotational motion plus linear motion. But before we start all that, we need to understand one concept, and that is nothing but concept of instantaneous axis of rotation. Okay, instantaneous axis of rotation. Now, what is instantaneous axis of rotation? Okay, see, we have seen car rolling on the ground. So whenever a car rolls on the ground, or the tire of a car rolls on the ground, okay, suppose this car is rolling with angular velocity omega. Okay, angular velocity omega. Now, if I see this point in the car, okay, this point in the car, this point in the car, what is the velocity of this point as observed by someone on the ground? The velocity of this point is zero. Okay, now suppose this car is rolling with angular velocity omega, and we know that rolling motion is nothing but a combination of rotational motion plus linear motion. Okay. Okay. Now, if someone asks me what is the velocity at topmost point, the velocity at topmost point as observed by someone on the ground is nothing but omega r, or velocity due to rotational motion, plus v. What is the velocity at this point? It is nothing but omega r in downward direction plus v in rightward direction. What is the velocity at this position at point of contact with the ground? It is nothing but omega r towards left and v towards right. What is the velocity at this point? It is nothing but omega r towards top and v towards right. Okay. So if you observe a rolling motion, okay, there exists a certain point in the tower where the velocity at that point is equal to zero. Okay, and any axis that passes through that point is called instantaneous axis of rotation. Okay, so let me write down the definition. Axis that passes through the point which has zero velocity, is called instantaneous axis of rotation. Instantaneous axis of rotation. See, I just call this the axis passing through this point as instantaneous axis of rotation, but that is not always the case. Okay, always this point that touches with the ground, or the part of the tire that touches with the ground, might not have zero velocity. For example, suppose I'm rolling with very high speed and I slam the brake. That means what? This point is sliding off the ground, and at that position, this point, or the point that touches the tire with the ground, won't have zero velocity. Understood? So instantaneous axis of rotation has a fixed definition, and that fixed definition is whichever point in this circle or in this tire has zero velocity, and any axis passing through that point, okay, is called instantaneous axis of rotation. Understood this much? Now see, I have drawn two omega out here. One omega is nothing but this omega, or this omega as I have shown out here. Okay, angular velocity as seen from this axis of rotation, or instantaneous axis of rotation, and another one angular velocity that passes through the center. Okay, my question is, what is the relation between this omega and this omega? What is the relation? See out. Okay, the relation between this omega and this omega is nothing but same. What do I mean by that is, see, if I take my observer, okay, see, who was observing this velocity? Omega. This omega was observed by someone that was on the instantaneous, or that was on the ground, isn't it? Now this omega is observed by someone that is sitting on the instantaneous axis of rotation. Okay, that is sitting on the top of the disk. Okay, and the value of this omega, or the magnitude of this omega as seen by someone on the ground, should be equal to the magnitude of this omega as someone sitting on the instantaneous axis of rotation. What do I mean by that is, suppose the wheel is, or suppose a car is going with 100 meter per second or 100 kilometer per hour. Okay, we convert that into meter per second and it comes to be some meter per second. Okay, that means the wheel is rolling with certain angular velocity, and let that angular velocity be 25 radians per second. Okay, who is observing this angular velocity? Someone on the ground. Okay, now if I pick my observer and put him at the instantaneous axis of rotation, okay, he'll see the center. Or if I pick my observer and put him in the, sorry, not center, put him in the center of the disk. Okay, he will see the wheel rotate with same angular velocity as 25 meters per second. Okay, let me look it up. Suppose a car is going with 100 kilometers per hour and the wheel is rotating with 25 meters per second. Okay, that angular velocity 25 meters per second is seen by someone on the ground. Now, if I take a observer and put him at the center of the disk, the angular velocity seen by the observer at the sitting on the center of the disk is nothing but same 25 meters per second. So the angular velocity through instantaneous axis of rotation as seen by someone on the ground is same as angular velocity of the wheel through the center as seen by someone sitting on that disk. So if this is 25 meters per second, this is also 25 meters per second. What is the net velocity at this point as seen by someone on the ground is nothing but omega r plus v. That means for this diagram, every point is moving with v. Now this point is also moving with v. This point is also moving with v. This point is also moving with v. So if I ask the what is the net velocity of this point as seen by someone on the ground, it is nothing but omega r upward and v in this direction. Understood? This is nothing but omega r. This is nothing but omega r. Omega r in this direction. Velocity at every point at omega r in this direction. Okay. And if a certain point has zero velocity, okay, that means the value of omega r is equal to the value of v. Not necessarily. If a certain point in this uh, tire or in this wheel has zero velocity and the axis passes through that point is known as instantaneous axis of rotation. We got this much? Okay. Now let us analyze our rolling motion. I can analyze this rolling motion in two methods. Method one is I can analyze this rolling motion as a combination of rotational motion and linear motion. Okay. So if I want to find out, suppose the wheel is rolling, method one, or let me write down method one. Okay. Suppose a wheel is rolling with angular velocity omega. Omega. Okay. So method one is what is the angular velocity to the center as someone as what is the angular velocity seen by someone sitting on the center is nothing but omega plus this linear velocity g. Okay. And if our instantaneous axis of rotation is outside, we'll get the relation between v and omega. Okay. How? See, instantaneous axis of rotation has zero velocity. We know this much. Okay. And this wheel is rotating with angular velocity omega. So if I find out the distance between center and instantaneous axis of rotation and name that r. Suppose this is the distance between center and instantaneous axis of rotation. Okay. We know that v is equals to omega into r. Okay. This instantaneous axis of rotation is not precisely touching the ground. Now there are various kind of things. First, what is the total kinetic energy? Total kinetic energy is equals to total kinetic energy is equals to half I omega square. Okay, rotational kinetic energy plus half mv square. Linear kinetic energy. Okay, what is the total momentum? Total momentum is nothing but angular momentum. Okay, or angular momentum due to this wheel plus linear momentum out there. What do I mean by angular momentum itself? How can you add up angular momentum and linear momentum together? Both are different units. No? So it's not like that. If I want to find out total momentum or total linear momentum, total linear momentum. What I'm actually finding out is total linear momentum as from the instantaneous axis of rotation. Okay, it is nothing but mvr or uh, m into v into r, or let's say mrv or I omega plus mr cross v. And this is not total linear momentum. I made a mistake out here. Total angular momentum. Okay, total angular momentum is equal to I omega plus rotational momentum due to this one m into r cross. Understood? This one is the total angular momentum. Okay. R means nothing but radius of the wheel. Or not radius of the wheel, the point between instantaneous axis of rotation and the center of the wheel. Okay, this is the value of R. Okay. Now we discuss method 2. Method 2 of analyzing the same thing. Method 2 of analyzing the same thing is nothing but suppose this wheel was rolling. Okay. Suppose this wheel, this is the point where zero velocity occurs. This is the center of the wheel. Angular velocity is omega. This is the rotor. Okay. And rotational motion is a combination of linear motion and rolling motion. Not rolling motion, rotational motion. Rolling motion is a combination of linear motion and rotational motion. But out here, while we're analyzing this one, okay, we do not need to divide into rotational motion and linear motion. We can directly analyze it from there. Okay, how? Suppose I want to find out the total kinetic energy. Total kinetic energy. Okay, total kinetic energy is nothing but moment of inertia passing through this point. Okay, half I omega square. I is nothing but moment of inertia passing through instantaneous axis of rotation. Okay, out here, whenever I say moment of inertia, I omega square, this I is nothing but moment of inertia passing through the center of the disk. This I is nothing but moment of inertia passing through the center of the disk. Whereas if I take the I out here, this I out here is nothing but moment of inertia passing through the instantaneous axis of rotation. Similarly, total angular momentum is nothing but I on moment of inertia passing through the instantaneous axis of rotation into angular velocity. Okay, moment of inertia passing this I out here is nothing but moment of inertia passing through the center. Okay, this I, whenever I'm analyzing my method 1, my moment of inertia is nothing but moment of inertia passing through the center. And whenever I'm analyzing my method 2, okay, if I just take I omega, that means my moment of inertia is calculated through the instantaneous axis of rotation. Okay, and if I calculate this value by method 1 and this value by method 2, both my answer will come as same. Okay, we'll see that later in the program. Now, let me introduce the concept of pure rolling. Okay, concept of pure rolling. Concept of pure rolling is nothing but when this instantaneous axis is nothing but at the point of contact. Okay, when this instantaneous axis of rotation or this point, but velocity is equal to 0, which is the point of contact. Okay, that means if a body is rolling, okay, and this point, the point of contact between the tire and the ground, okay, has 0 velocity. That means my instantaneous axis of rotation passes throughout it. That is at that point concept of pure rolling occurs. Okay, so if I give my omega out here, okay, I can easily say that linear velocity or velocity that passes through the center of mass, v is equals to omega. This is the condition of pure rolling. Condition of pure rolling. Understood this much? And we can analyze this pure rolling by concept of method 1 on concept of method 2. One more thing we must learn about rolling motion is that friction force is necessary for rolling. Okay. In case of pure rolling, even in case of pure rolling, friction force is required. Friction force is necessary for rolling. Okay. However, okay, the work done by friction force in rolling motion or pure rolling motion is 0. Work done by friction force in pure rolling is equals to 0. Okay, and if it is not pure rolling, that means the part that touches with the ground slides somewhat a little, that is nothing but impure rolling. Okay, so in case of impure rolling, work done by friction force can be positive or negative, whichever the case that is. Okay, so in case of pure rolling, see, whenever rolling motion is there, that means friction force is there. Okay, in case of pure rolling, work done by friction force is equals to 0. In case of impure rolling, that means sliding plus rolling, or the instantaneous center of axis or instantaneous axis of rotation is not at the center or not at the point of contact. Okay, during that time, work done by friction force might be something else. This much is understood. Let's see what you have done. Rolling motion. Rolling motion is a combination of rotational motion and linear motion. Okay, an instantaneous axis of rotation, a point that has 0 velocity. We can analyze rolling motion by two methods. One is kind of the instantaneous axis of rotation. Okay, or v is equals to omega into r, but v is nothing but linear velocity as observed from or linear velocity of center of mass of the wheel. Okay, and omega is nothing but angular velocity as observed by someone sitting on the center of this. Okay, v is equals to omega into r. R is nothing but distance between instantaneous axis of rotation and center. Total kinetic energy is equals to half I omega square, or half I from the center into omega square plus half mv square. Okay, and total angular momentum is equals to I omega plus m into r plus v. Okay, mrv. Okay, what is the velocity at this point? It is nothing but omega r plus v. Velocity at this point is nothing but omega r plus v. Velocity at this point, bottommost point, is nothing but omega r plus G means the vector summation. Omega in this direction, velocity in this direction, you have to subtract them both. Okay. And method 2 is nothing but analyzing your kinetic energy and momentum from the instantaneous axis of rotation. So if you take your momentum throughout here, so if you take your moment of inertia throughout here, you directly write the angular velocity out here. You need to put the pattern of linear velocity. Okay. Then study the concept of pure rolling. Pure rolling is a case where the instantaneous axis of rotation touches the point of contact. And V is equals to omega r, where r is equals to radius of the tire. Okay. That is the condition for pure rolling. This was yesterday. Now let us solve some problem. Okay. Now let us see how we apply the concept of rolling motion to this question. Okay. This question is same as before. There is an elevator. Okay. And inside this elevator there is a string. And this string is tied to a cylinder. Okay. And this elevator is moving up with acceleration W0. We have to find out the acceleration of this cylinder with respect to the CCTV outlet. Okay. So this question is same as the previous question that I have done. But the thing that I'm going to do out here is I'm going to solve this question by two different methods. Okay. The first one is method one out here. Okay. Rolling motion is nothing but combination of rotational motion plus linear motion. The second motion or the second concept that I'm going to use is instantaneous axis of rotation. Okay. So if I draw the free body diagram of this cylinder, let's see. Okay. Let's draw the free body diagram of the cylinder. mg. Okay. This pseudo force also. Pseudo force is nothing but mass of the cylinder into acceleration of the frame in opposite direction. So m omega naught. Out here there is tension force. And this out here is the acceleration of the cylinder as seen by CCT. Okay, since we have applied pseudo force. Okay. Now method one. That means I am going to apply rotational motion and this linear motion separately. Okay. Method one. See, while the cylinder is coming down, it is also rotating with angular acceleration alpha. Okay, and this alpha of the disc, this alpha is seen by someone sitting on the middle of the disc, isn't it? So let me write down the equation. What is the force equation? Force equation means mg plus m omega naught minus t is equals to m. So force equation is mg plus m omega naught. So I take m common, mg plus omega naught minus t minus this t is equals to mass into acceleration. This is my equation one. My equation two would be torque equation. The first equation that I made out here is nothing but force equation. Force equation. Okay. Force equation. The second equation I'm going to make is nothing but torque equation. Torque equation means I'm going to see the center. I'm going to see the center. Total torque. Okay. As observed from the center is equals to moment of inertia of this disc and thing. So if I see that the center, what is the torque due to mg force? 0, because the mg force is passing to the center. Similarly, torque due to this pseudo force is also 0. And there exists a torque due to tension force. So torque due to tension force is nothing but T into R is equals to I alpha, where I is equals to moment of inertia of the cylinder through the center, m square by 2 into alpha. Okay, this is my equation number 2. Understood? Now see. At this position also, I need to remember that if I observe this point, that means this point, the velocity of this point is equal to 0. That means this point is the instantaneous axis of rotation. So if this point is the instantaneous axis of rotation, can I say A is equal to alpha into R? See, if you observe this point has 0 velocity. And what did I say? What did I say about relation between instantaneous axis of rotation and R? See, V is equal to omega R, A is equal to alpha R, where R is nothing but how much? Distance of center from the instantaneous axis of rotation. See how R. Okay. So let's continue the question. So if I know the instantaneous axis of rotation, and if I know the instantaneous axis of rotation to be this one, I can easily say A is equal to alpha into radius of the cylinder. Or A is equal to alpha R. Okay. By using this equation, I can say alpha is equal to A by R. So this alpha is nothing but A by R. So I can get tension into R is equal to m R square by 2 into A by R. R and R will get cancelled, R and R will get cancelled. So tension force is equal to m by 2. If I substitute the value of tension force out here, I'll get the value of acceleration. So if I substitute the value of tension force out here, what do I get? M into G plus omega naught minus ma by 2 is equals to ma. I just substitute the value of tension force out here. Okay, or m into g plus omega naught is equals to ma plus ma by 2. This is nothing but c ma by 2. M and m would get cancelled, or acceleration would be 2 by 3 g plus omega naught. Or acceleration of this cylinder as seen by some of the CCTV is nothing but 2 by 3 g plus omega naught. Okay, and tension force is nothing but m by 2 into acceleration. So tension force is nothing but m by 2 into acceleration, and acceleration is nothing but 2 by 3 g plus omega naught. 2 by 3 into g plus omega. Okay, this 2 and this 2 get cancelled. Or tension force is equals to m by 3 g plus omega. This much is understood. Okay, now solve the same equation from by method 2. By method 2 means by this method. Okay, when I know, see, I'm solving the same equation by method 2. Method 2 means I'm taking my moment of inertia from instantaneous axis of rotation. So this was my method 1. This is my method 2. Method 2. So while applying method 2, we are not taking moment of inertia from instantaneous axis of rotation. We do not need to apply force equation, or there is no logic of using force equation or linear equation. Okay, see, if I apply my equation from here, there will be only one equation, and that is nothing but torque equation or rotational equation. Okay, so whenever you are applying equation from instantaneous axis of rotation, always remember there is no linear equations. Okay, no linear equation, or only rotational equations. Only rotational equations are used. Rotational equations. Okay, what do I mean by only rotational equations? See, what is the moment of inertia throughout here of this point? M square by 2 plus m square, 3 by 2 m square. Okay, so if my axis is passing through this point, what is the torque? Torque is due to nothing but mg plus m omega naught. So torque is nothing but mg plus m omega naught. See, now my instantaneous axis of rotation is passing through this white cylinder. Okay, mg plus m omega naught. That means torque is caused due to these two forces. Okay, into r is equals to I omega. What is the moment of inertia about this axis or about this axis? It is nothing but mr square by 2 plus mr square. Okay, if I apply parallax theorem, mr square by 2 is the moment of inertia to the center plus mr square into parallax theorem into alpha. Okay, out here also when I use method 2, I must remember a is equals to alpha into r, where a is nothing but acceleration or linear acceleration of the body. Alpha is nothing but the rotational acceleration of the body as observed through center of mass, which is equals to the angular acceleration of the body when observed from ground. Okay, into r. Okay, so this equation is valid for method 1. This equation is also valid for method 2. So by this equation, you know that alpha is equals to a by r. A by r. And whenever you're writing a is equals to alpha r for an equation, no, always remember this r is the distance from center of the body to instantaneous axis of rotation. It is the instantaneous axis of rotation might not always be the edge. Okay, it might be any point. Okay, so always remember this r is nothing but distance from center to instantaneous axis of rotation. Now the problem becomes simple. Okay, m into g plus omega naught r. If I take m r square, m r square plus m r square by 2, nothing but 3 by 2 m r square. So let me write this as 3 by 2 m r square into a by r. So r and r will be cancelled. M and m will be cancelled. Acceleration is equal to 2 by 3 g plus omega. Okay. And tension force. What is the value of tension force? Tension force. Let's see. Okay. If I use tension force from first equation, okay, tension force I'm using from first equation. Tension force is equal to m by 3 g plus omega. Tension force is equal to m by 3 g plus omega. The main thing that you need to understand the difference between method 1 and method 2. Method 1, I apply my moment of inertia to center of mass. Okay, and whenever I apply method 1, I must apply two equations. First one is the torque equation or rotational equation. The second one is the force equation or linear equation. That means out here I am considering the total rolling movement is due to rotational movement and translational movement. But when I'm applying method 2, okay, to the instantaneous axis of rotation, my only consideration is there is only rotational movement. There is no translational movement separately out here. Understood? When I'm observing through instantaneous axis of rotation, there is no translational movement out here. Okay, you must take that into account, or you must remember that. So this is our question number 1.254 of it. Now let's see the next problem. Okay, out here there is a rope connecting a bigger cylinder, and this bigger cylinder is attached to a smaller cylinder, and this rope is wound around this smaller cylinder. Okay, so and this surface out here is frictionless. There is no friction in this surface. So if there is no friction in this surface, can you determine the direction of rolling? Of course, the direction of rolling is same as you assume without friction. So if there is no friction, okay, this ball, this cylinder will rotate in this anti-clockwise direction, isn't it? So the direction of rotation is nothing but anti-clockwise. This is the direction of rotation. Okay, see, there are only thing holding this cylinder is nothing but this rope, and this surface out is frictionless. So this surface is supposed to rotate like this, no? Okay, so this is the direction of rotation. Yeah, right. Now what we need to find it out here? We need to find out find the acceleration of spool axis. That means we need to find out what is the acceleration omega. Okay, so we do a simple method. The first one is this is the instantaneous axis of rotation. That means while this body spins, if I observe this point for just a time frame, that means the acceleration of the velocity, not acceleration, the velocity of this point is equal to zero. Okay, and we know that okay, v or linear velocity v is equal to omega into r, where r is small r, and we also know that a or acceleration. Achha, let me write this A. Okay, instead of using irodov notations, I'm going to use normal notation. Okay, let's just normal notation. This is nothing but A. Okay, A is equals to alpha. If I know this by observation that this is the instantaneous axis of rotation, I know that V is equals to omega, A is equals to alpha. Okay, now my choice is do I want to write my equation from center of the disk or do I want to write my equation from instantaneous axis of rotation? Okay, let's see the question. The moment of inertia relative to its own axis I. That means the moment of inertia through this axis is given. So whenever I'm writing my equation from this center axis, I must consider two motions. First one is the rotational motion, the second one is the linear motion. Okay, so my rotational equation. See, if my observer is sitting at the center, there is torque due to this tension force. Okay, torque due to this tension force. Okay, torque and mg force is acting in this direction. Torque due to this mg force is zero. Okay, and see, this mg force is divided into mg sin alpha and mg cos alpha. So torque due to mg force is already zero. Why? Because I'm observing the torque through this axis or the axis that is passing through center. Okay, so TR is equals to I alpha. I into alpha. Or I is equals to 0.45. I'll substitute the values there. Okay. We know that alpha is equals to A by R. Where A is nothing but acceleration or rotational acceleration. R is nothing but distance from instantaneous axis of rotation to the center of the disk. Okay. Or out here. TR is equals to I into A by R. Okay. Okay. Or tension force is equals to I into A by R square. Now, if I draw a second equation, see, whenever I'm applying my thing through center of whenever I'm observing my equation to center, that means there are two equations. First one is the rotational, second one is the translational. So, translational equation. Translational equation. Translational equation is nothing but net force is equal to mass in translation. So, mg sin alpha minus t. Mg sin alpha. This is the value of alpha minus t is equals to m into a. Okay, the value of t is already found out here, I alpha by r square. So if I substitute the value of t out here, what do I get? Mg sin alpha minus I alpha by r square is equals to m. Okay, now point of inertia is given, mass is given, r is given. We just need to find out the value of a. Or mg sin alpha is equals to ma plus ia by r square. If I take a common, m plus I by r square. If I take a common, m plus I by r square is equals to a. Okay? Or a is equals to mg sin alpha divided by m plus I by r square. And all the values are given. Okay? Now suppose I have to solve the same problem but from the moment of or from the instantaneous axis of rotation. Okay. So suppose I'm solving my problem from instantaneous axis of rotation. Okay. So when I'm seeing the problem from instantaneous axis of rotation, there will be only one equation and that is nothing but the rotational equation. Rotational equation. Okay, see, E is equals to omega r and E is equals to alpha r. This is valid for both method 1 and method 2. Okay, now when I'm seeing rotational component of the equation, okay, if I'm seeing out here from my observatories or my axis of rotation is out here, and what is causing the torque is nothing but mg sin alpha, isn't it? Mg sin alpha is causing a torque, okay, and P force, the torque due to tension force is equals to 0. So mg sin alpha into r. R is nothing but torque. Okay, mg sin alpha force into r. Okay, the torque due to mg cos alpha would be 0 because angle between r vector and mg cos alpha is equals to how much? 0. Okay, so torque is only caused due to mg, this component of gravity force, mg sin alpha. Okay, so torque is nothing but mg sin alpha into r. And fine is equals to I alpha. What is the value of I? The moment of inertia through the center is given as this capital. Okay, moment of inertia through the center is given as capital. If I apply parallel axis theorem plus m r square into alpha, isn't it? And you already know that a is equals to alpha into r, or alpha is equals to a by r, or mg sin alpha into r is equals to I plus m r square into a by r. Okay, now if I take r square common, or a is equals to mg sin alpha into r divided by r square. If I'm cancelling this r, I'm taking this square out here. Divided by I plus m r square. Got it? Is equals to a. Now if I divide this r square out here and out here, I'll get a is equals to mg sin alpha divided by I by r square plus m is equals to a. I just divided this r square in the denominator. And this answer out here is same as the previous answer that we got. See? Understand? So it doesn't matter which method you use as long as you keep your observation correct. That means when I'm using instantaneous axis of rotation, torque is caused due to this one. Okay, and there is no linear component of equation. When I'm using means when I'm using center of or moment of inertia to the center, or when I'm using this axis of rotation that passes through the center, I must use two equations. First one is the rotational equation, second one is the translational equation. In rotational equation, okay, torque is called tension force, and translational equation mg sin alpha minus t is equals to m. Understood? So both methods are the same. So let's start with our next question. In this question, there is a cylinder kept on this surface. The coefficient of friction between the surface and the cylinder is given as m. Okay? Instead of using k, we'll be using m. Now the question is asking, what is the maximum force that I can apply out here or pull this string such that this cylinder rolls without slipping? Okay, so let's draw a diagram. This is the cylinder, this is the rope, and applying force out here. Okay, now my first question is, what is the direction of friction force? Okay, to find out the direction of friction force, here is a small trick. The trick is assume that there is no friction. Okay, and after assuming no friction, find out the direction of rotation. Once you get the direction of rotation, then look at the surface. In which direction is the surface trying to slip? The friction force will opt in opposite direction. Okay, so make a note or make a trick that to find out the direction of friction force in rolling motion, to find the direction of friction force. First, we have to assume that there is no friction. First, assume no friction, no friction, and find out the direction of rolling or find out the direction of rotation. And find out the direction of rotation or motion. Okay, so out here, if I pull this one, okay, this thing will try to rotate in clockwise direction, isn't it? Will try to rotate in clockwise direction. So if it tries to rotate in clockwise direction, the bottom surface tries to slip in this direction, no? So friction force will act in the opposite direction. Understood? Now the question is, what is the maximum value of friction force? The limiting value of friction force is nothing but mu into n, isn't it? And if I apply perpendicular or vertical laws of motion or vertical equation for laws of motion, n normal contact force minus mg minus f is equals to 0, or normal contact force is equals to f plus m. So from this diagram I can get the value of normal contact force. So the value of limiting force out here, or limiting value of friction force out here, is nothing but coefficient of friction into F plus mg. Where F plus mg is nothing but the normal contact force. Okay. Now listen to me very carefully. This is the limiting value of friction force. Okay. Suppose I pull this strip, what would happen? The block would try to roll, and if I pull it much more bigger, what would happen? It would try to roll faster. What is stopping the sliding from happening? That means while rolling, okay, friction force acts in this direction. What is trying to prevent this surface from slipping? The friction force, isn't it? That means my net external force or my net external torque should be greater than or should be lesser than equals to friction force. That means my net external torque. That means whatever force I'm pulling out here, whatever that force causes, rotation, okay, that force into R, okay, would act in this direction. That force into R should be greater than the limiting value of friction force. Then only I'll get the maximum value of force. No, understood? So if I do torque analysis, okay, about the center, so torque analysis about the center. The positive torque out here is nothing but F into R. Okay, this rotates in clockwise direction, and negative torque out here is nothing but friction force into R minus friction force into R. Okay, is there any other force that is causing the torque? No, Mg passes through the center, so torque due to Mg is equal to 0. Normal contact force also passes through the center, so torque due to normal is also 0. Is equal to moment of inertia of the cylinder, which is nothing but mr square by 2 into angular acceleration of the cylinder. So if I take R common, F minus friction force is equals to mr square by 2 into alpha. Okay, or what is the value of friction force? The value of friction force is nothing but mu into F plus mg. That is the limiting value of friction force, isn't it? Or R into F minus how much? Mu into F plus mg is equals to mr square by 2 into alpha. Okay, and for pure rolling, we know that the condition, the instantaneous axis of rotation is at the point of contact. That means alpha is equals to, sorry, a is equals to alpha. That means if the acceleration of the center of the wheel is a, the relation between a and alpha is nothing but a is equals to alpha. If the velocity of the center of wheel is v, okay, then v is equals to omega r. For pure rolling, the instantaneous axis of rotation shifts to the surface contact or point of contact. That means the instantaneous axis of rotation is out here. Okay, and then we get the relation a is equals to alpha, where r is the radius of the cylinder. Okay, so if I substitute the value of alpha out here, the value of alpha is nothing but a by r, isn't it? So this value of alpha is nothing but a by r. If I cancel out r from out here, I get my torque equation as f minus mu f plus, sorry, minus mu mg. Okay, I just expanded this term. F minus mu f minus mu mg is equals to ma by 2. Ma by 2. Okay, or if I take f common, 1 minus mu mg is equals to ma by 2. Or if I do the equation out here, okay, let me draw the equation out here. Let me bring this equation to the next page. Okay, bring this equation to the next page. Or f into 1 minus mu, f into 1 minus mu into minus mu mg, sorry, minus mu mg should be equals to how much? Should be equals to ma by 2. Or f into 1 minus mu is equals to ma by 2 minus or plus mu mg. Or f should be equals to ma by 2 plus mu mg divided by 1 minus mu. The problem with this equation is I have the value of acceleration, and I still do not know the value of acceleration in this equation. Okay, so how do I find out the value of acceleration? See, if I use torque equation, I can also use force equation. Okay, torque equation is nothing but rotational equation. Force equation is nothing but linear equation. And why can I use both of them? Because I'm analyzing the thing from center of mass, not center of mass, from the center of the wheel. Okay, so if I do my force equation, okay, force equation, force equation. Okay, my question is, what is the net force in horizontal direction? Friction force, isn't it? Is there any other force in horizontal direction? No. So friction force is equal to mass into acceleration. So friction force is equals to mass into acceleration. And what is the limiting value of friction force? Mu into F plus mg. Mu into F plus mg is equals to mass into acceleration. Okay, so this is my equation 1. This is my equation 2. solving these two equations, I can get the value of force and I can get the value of acceleration. So let's just solve this one. Ma is equals to mu into F plus mg. So the substitute is Ma. Okay. Okay. What do I get? Force is equals to Ma by 2 or mu into F plus mg. Okay. By 2 plus mu mg divided by 1 minus mu. 1 minus mu. Or let me just solve this quickly. Okay. F into 1 minus mu is equals to mu F plus mu mg by 2 by 2 plus mu mg. Okay. Or F minus mu F is equals to mu F by 2 mu mg plus mu mg is nothing but 3 by 2 mu mg plus 3 by 2 mu mg. If I bring this mu F to the left hand side, I'll get F minus mu F minus mu F by 2 is equals to 3 by 2 mu mg. Mu F minus mu F is nothing but minus 3 by 2 mu F. Or F minus 3 by 2 mu F is equals to 3 by 2 mu mg. Or if I take F common, F is equals to 1 minus 3 by 2 mu is equals to 3 by 2 mu mg. Or if I solve the equation, F is equals to 3 by 2 mu mg divided by 1 minus 3 by 2 mu. Okay. I can either simplify the equation or leave the answer as it is. So the maximum force that I can apply out here without slipping is nothing but this value of force. Now if I get the value of force, I can easily get the value of acceleration. Friction force is equal to mass into acceleration. Okay. Okay. The value of friction force is nothing but mu into F plus mg. So to find out the value of acceleration, if I use second equation, okay, mu into F plus mg. Let me write down the equation on the next page. Okay. I'm writing down this second equation. Mu into F plus mg is equal to m. Mu into F plus mg is equals to m. Or A is equals to mu into F plus mg divided by m. What is the value of force that I got? The value of force is nothing but this value. Okay, 3 by 2 mu mg by 1 minus 3 mu 1 minus 3 by 2 mu. Okay, or A is equals to mu into what is the value? 3 by 2 mu mg. 3 by 2 mu mg divided by 1 minus 3 by 2 mu divided by 1 minus 3 by 2 mu plus mg divided by m. Okay, so I can either simplify this parameter and find out the value of acceleration or leave it as it is. Okay, whichever you find it easier. See, uh, let's leave it as it is. Okay, so acceleration, the minimum value of acceleration is nothing but this one. Okay,